Have you ever seen a video online and had to watch it twice? Maybe it was a pop star dancing on stage, flanked by a crew of backup dancers. Their moves are perfect, almost too perfect. You look closer, and a strange feeling creeps in. Those aren't people, they're robots, moving with a grace that seems impossible for machines. Even for engineers and builders like me, who spend our lives around gears and circuits, it's a jaw-dropping sight. It makes you question what you're seeing. That's the magic and the mystery of modern robotics. These creations are blurring the line between metal and life, and it all starts with a single ambitious idea. This isn't just science fiction anymore. We are living in an age where the dream of building a mechanical person is becoming a reality, piece by piece, in workshops and laboratories all over the world. The goal is no longer just to make a machine that can perform a task, like welding a car door or vacuuming a floor. The new goal, the ultimate challenge, is to create a machine that looks, moves, and perhaps one day even feels like a human. It's an incredible journey of creation, one that combines the precision of engineering with the nuance of art, and it forces us to ask some really big questions about who we are. This process is a symphony of different disciplines. It requires mechanics, electronics, software programming, and even artistry. Think of it like the ultimate build project. You start with a blueprint, a vision of what this being could be. From there, you begin the painstaking process of bringing it to life, one component at a time. Each step presents its own unique set of problems to solve. How do you make a metal joint move as smoothly as an elbow? How do you make a silicone face show sadness or joy? Every single detail is a mountain to climb, and the view from the top is a walking, talking miracle of engineering. In this essay, I want to take you on a journey. We're going to step inside the workshop and explore how these incredible humanoid robots are born. We'll go from a simple metal frame to a complex being that can take its first steps into the world. I want to show you the nuts and bolts, the wires and code, but also the passion and the wonder that drives the creators. This isn't just about building a machine, it's about exploring the very definition of life itself. So, grab your safety goggles. We're heading into the lab to build a person from the ground up. Every great build starts with a solid frame. For a humanoid robot, this is the skeleton. We're not talking about a simple collection of metal rods. This is a highly engineered structure designed to mimic the human skeleton in both form and function. Engineers often use lightweight but incredibly strong materials, like aluminum alloys or carbon fiber composites, the same stuff used to build race cars and airplanes. The goal is to create a frame that is strong enough to support all the components that will be added later, yet light enough to move with agility and efficiency. It's a delicate balancing act. Each joint in this mechanical skeleton is a marvel of engineering. Think about your own knee or shoulder. It can bend, twist, and rotate with incredible freedom. To replicate that, engineers use a combination of bearings, gears, and swivels. These aren't clunky, noisy parts. They are precision-machined components designed for silent, smooth operation. The skeleton slowly takes shape on the assembly table, first a leg, then a torso, then an arm. It's an eerie and beautiful sight, like watching the fossil of a futuristic creature being pieced together for the very first time. You can already see the human form emerging from the collection of metal parts. The design of the skeleton dictates everything about the robot's potential for movement. Will it be able to run? Can it crouch down to pick something up? Can it turn its head to look over its shoulder? All of these capabilities are determined by the degrees of freedom designed into each joint. A human has over 200 degrees of freedom in their body, allowing for our amazing range of motion. The challenge for robot builders is to get as close to that number as possible, creating a machine that isn't stiff and clumsy but fluid and natural. As the final pieces of the skeleton are bolted together, a sense of anticipation fills the workshop. The frame stands on its own for the first time, a silent, metallic statue. It has no muscles, no skin, no brain. It's just the promise of what's to come. But even in this raw state, you can see the humanity in its silhouette. For the build team, this is a huge milestone. It's the moment the blueprint becomes a physical object, the first step in a long journey from an inanimate object to something that might one day be mistaken for a living being. The foundation is laid. With the skeleton complete, the next challenge is to give it the power of movement. A robot needs muscles, and in the world of engineering, these are called actuators. Instead of biological muscle fibers, we use a variety of technologies. The most common are electric motors, but these aren't the big, bulky motors you might imagine. They are compact, powerful micromotors, carefully embedded within the skeleton itself. When an electrical signal is sent to a motor in the robot's knee, it spins a series of gears that cause the joint to bend, just like your quadriceps contracting. These actuators are connected by a complex network of artificial tendons, often made from high-strength cables or belts. This system of motors and tendons is what allows for fine, controlled movements. It's the difference between a jerky, robotic arm and one that can delicately pick up an egg without breaking it. For fluid, dynamic motions like dancing, engineers use incredibly fast and responsive actuators that can change direction in a fraction of a second. It's a beautiful, intricate dance of electricity and mechanics, all hidden just beneath the surface, working together to bring the cold metal frame to life. Once the muscles are in place, it's time to give the robot its skin. This is where art truly meets science. The goal is to create a synthetic skin that not only looks real, but feels real too. Most often, this is done with high-grade silicone, a material that can be tinted to perfectly match human skin tones. Artists and technicians work together, adding subtle details that make all the difference. They paint on tiny imperfections like freckles, moles, and even faint bluish veins just beneath the surface, mimicking the way light passes through real human skin. The texture is just as important as the color. To replicate the feeling of skin, the silicone is often molded with microscopic pores and fine lines, just like the ones on your own hand. In some advanced prototypes, this artificial skin is even embedded with a network of tiny sensors. These sensors can detect pressure, temperature, and texture, allowing the robot to feel the world around it. When you see this skin being stretched over the mechanical frame, it's a transformative moment. The machine starts to disappear, replaced by a figure that looks uncannily human. It's both fascinating and a little unsettling. The face is where a machine truly begins to look like a person. It's the focal point of our interactions, the canvas for our emotions. Creating a lifelike robotic face is one of the most difficult and delicate parts of the entire build. The process often starts with a sculpted clay model, which is then three-dimensionally scanned to create a digital template. This template is used to build the underlying mechanics of the face. Beneath the silicone skin, a complex web of tiny motors and linkages is installed. These are the muscles that will control the robot's facial expressions. The eyes are often called the windows to the soul, and for a humanoid robot, they are critical for creating a sense of life. These aren't just glass spheres. They are intricate cameras, capable of focusing, tracking movement, and adjusting to light. They are set into sockets that allow them to dart back and forth, to blink, and to follow you as you move around the room. The simple act of a robot making eye contact is a powerful experience. It's a programmed behavior, of course, but it feels real. It's the moment the robot stops being an it and starts to feel like a who. The real magic happens when these facial mechanics are programmed to create expressions. A slight pull from a motor near the corner of the mouth creates a smile. A different combination of actuators furrows the brow in concentration or raises the eyebrows in surprise. Engineers and animators work together, studying human expressions and translating them into code. They program sequences for joy, sadness, confusion, and curiosity. Seeing the robot smile for the first time is a profound moment for the creators. It's a flicker of artificial emotion, a ghost of humanity in the machine that they have painstakingly built. This is often the point in the build where the team starts to form an emotional connection to their creation. Up until now, it was a collection of parts, a complex mechanical puzzle. But when the face is complete and the eyes look back at you, something changes. The engineers might start giving it a name. They talk to it, even though they know it can't yet understand. The robot is still just a puppet, controlled by a computer on a nearby desk. But the illusion of life is so powerful that it begins to feel like a colleague in the lab. The project has crossed a threshold from pure engineering into something much more personal. A beautiful body is nothing without a mind to control it. For a humanoid robot, this is the artificial intelligence system, its brain. This isn't a single object, but a powerful network of computers, processors, and software. This brain is often housed within the robot's torso or head, connected by thousands of wires that act as the robot's nervous system. These wires carry signals from the brain to every motor and actuator, and they carry information back from the robot's sensors, its eyes, ears, and touch-sensitive skin, to be processed. The software that runs on this hardware is incredibly complex. It's broken down into layers. At the most basic level, you have the motor control systems. This is the software that handles balance, walking, and object manipulation. It's constantly making millions of tiny calculations per second to keep the robot from falling over. It adjusts the angle of the ankle, shifts the robot's weight at the hip, and swings the arms for balance, all without conscious thought. Much like our own cerebellum handles our movements. It's the silent, tireless workhorse of the AI. On top of that, you have the cognitive and interactive layers of the AI. This is where the robot begins to think. This software processes the data from its cameras and microphones, allowing it to recognize faces, understand spoken language, and interpret the world around it. Using machine learning algorithms, the robot can learn from its experiences. For example, if it fails to pick up a cup, it can analyze the sensor data from the failure and adjust its grip the next time. It's a slow process of trial and error, a digital childhood where the robot learns the fundamental rules of physical reality. Installing this brain and booting it up for the first time is the true moment of birth. The lights in the eyes flicker on. The actuators hum with potential energy. The robot, which was once a lifeless puppet, is now a self-contained entity. It can stand on its own, perceive its surroundings, and begin to make its own decisions based on its programming. For the engineers who have poured months or even years into the project, this is the climax. The ghost is finally in the machine. Their creation is no longer just a collection of parts. It is an autonomous being, ready to take its first step. The robot stands in the center of the lab, untethered for the first time. A command is sent: walk. Inside its AI brain, complex algorithms fire, calculating the perfect sequence of movements. A leg lifts, swings forward, and plants itself on the floor. The body's weight shifts, and the other leg follows. It's a slow, deliberate, almost clumsy gait at first, but it is walking, all by itself. In the room, the creators hold their breath. This is more than just a technical success. It feels like witnessing a historic moment. The machine they built is moving through the world under its own power, driven by its own artificial mind. This is just the beginning of a long learning process. The robot will spend weeks, months, or even years refining its movements, learning to navigate new environments and interacting with people. Each interaction teaches it something new, adding to its growing database of knowledge. This is where we, as creators and observers, begin to wonder about the future. What will these beings mean for humanity? Will they be our assistants, helping with tasks in our homes and workplaces? Will they care for the elderly, explore dangerous environments, or become creative partners in art and science? The possibilities are as vast as our imaginations. Of course, this journey also raises profound ethical questions. As these robots become more and more lifelike, how will we treat them? If a robot can express sadness, does that mean it can feel sad? At what point does a simulation of life become a form of life itself? These are not easy questions, and we don't have the answers yet. We are charting new territory, and we must proceed with curiosity, but also with caution and a deep sense of responsibility for the beings we are creating. They will be a reflection of our own values, our own humanity. It's important to remember that much of this is a creative vision, a look at what could be. The technology is advancing at an incredible pace, but we are still in the early days of this revolution. The future is not written. The humanoid robots of tomorrow might be our friends, our helpers, or something else entirely that we can't yet even conceive. What is certain is that the journey of creating them, of taking metal, wire, and code and breathing into it a spark of artificial life, will continue to be one of the most exciting and challenging adventures in human history. This video combines real robotics principles with a creative cinematic narrative to explore how humanoid robots are imagined and developed. Some elements are simplified or speculative and are not intended as literal representations of current technology.